to us about Yamanouchi toppling.
So, first of all, let me thank all the organizers to give me this great opportunity. Well, I'm going to explain you what is Yamanouchi toppling and why we are interested in this game. My talk is based on joint paper with Nobel Correa, he's here, and Domenico Senato. Well, what is Yamanouchi toppling? Essentially, we deal with some variants of the well-known chute-firing game. We encode this game by means of an action of a certain group that we have called the toppling group. Then we have orbits. We associate these orbits series that are generating function, and by means of a linear operator, we are able to systematic connection. To give a systematic connection between toppling games, or if you prefer, chute-firing games, and classical symmetric function theory. Well, at the end, I will also mention something about orthogonal polynomial system. I mean, exactly the same setting can be applied directly to give combinatorial treatment of classical orthogonal polynomials, and at the end of my talk, I will have some minutes, some time. I will also mention some further developments. So let me recall what is a configuration on a connected graph. A configuration simply is a map associating each vertex of the graph with an integral weight. This is our first little difference between classical chute-firing game that in general uses only non-negative weights. When we fire a vertex, then this produces a toppling of its weight. I mean, the weight of the fired vertex V will decrease by the number of neighbors of V, and simultaneously the weight of each neighbor of V will increase by 1. So, a simple example, here we have a connected graph. You see the configuration. We want to fire the vertex in red. We see 3 neighbors, so 5 will become 3, and the other 3 vertices will increase their weight by 1. So from the starting configuration, we obtain a further configuration. To easy our notation, we will always assume that vertices are denoted by the first time positive integers. So configurations can be identified with arrays of integers, where the ith entry is the weight of the vertex I. So we have a relation on z to the n. We say that alpha is equivalent to beta if and only if we can obtain beta from alpha by means of a suitable firing sequences. This is a well-known relation of equivalence that has been studied from many different points of view. Starting from physical context related to Sampine models, then very recently elliptic curve, an analog of the Riemann-Roch theorem stated for graphs. So a well-known relation of equivalence. We will look at this stuff from a more algebraic point of view. So simply think of firing the vertex I as a map defined from z to the n to z to the n. So we have a toppling map for each vertex, and we define the toppling group to be the group generated by toppling map. Well, the group acts on z to the n. We have orbits, and these exactly are the classes of toppling equivalences. This means that alpha, a configuration alpha, is equivalent to a configuration beta if and only if there exists a product of toppling maps that send alpha to beta. So this is the first structural properties related to G. I mean, the group algebra over complex number of the toppling group is always isomorphic to this quotient. It is essentially due to the fact that we only have 2 kinds of relation, commuting, and the product of all toppling map always is 1, the identity. This has one main consequence, for our purpose, we are able to recover the unique reduced decomposition of each element in the toppling group. I mean, choose an element in the toppling group, then there exists a unique array in capital IN. Capital IN consists of arrays of non-negative integers with at least one zero entry. So there exists a unique array in capital IN, such that G is equal to T to the A. So T to the A is the reduced decomposition of G. Well, we are ready to define our game, but before, let me define a modified version of toppling equivalence. We say beta less than alpha if and only if beta is T lambda of alpha. This time, T lambda is the reduced decomposition of a given element in the toppling group, a certain element in the toppling group, but lambda has to be an integer partition. I mean, in the reduced decomposition, T1 occurs lambda 1 times, T2 lambda 2 times, and so on, and lambda 1 greater than lambda 2 greater than so on. So it can be shown this is a partial order on Z to the n, and in particular it is a partial order on each orbit of the action of the toppling group on Z to the n. So this is our game. Assume that two configurations are given, say alpha and beta. Alpha is the starting configuration on the graph. We have a final configuration which is known being less than alpha, and assume that the player is asked to move from alpha towards beta by means of shortest firing sequences, and assume that the player has to obey the following prescription. I mean, when he fire a vertex, the player has to be sure that the resulting configuration, say gamma, still is less than the starting configuration alpha. So how we can characterize the set of all shortest firing sequences that solve this game? Well, a moment thinking will convince you that, well, if beta is less than alpha, there exists a unique element in the toppling group sending alpha to beta. This element must have a reduced decomposition of type T to the lambda. So the size of this partition will say as the length of all shortest sequences of fired vertices. And in order to obey our prescription, we need that in this array of positive integers, well, if we regard this array as a word over positive integer, this must be a Yamanouchi word of type lambda. So this is why Yamanouchi toppling game. And this is why we have a coding for the solution of this game. I mean, each firing sequences of shortest length for each standard Young tableau shape lambda. So we have a partial order. We may consider the dual order. We may define a dual version of the game where less than is replaced by greater than. So how we can find a solution of the dual game? Simply by looking at reduced decomposition of an inverse of a T lambda. It is not difficult to show that if you have a T lambda that map beta to alpha, the inverse of T lambda has a reduced decomposition of type T lambda tilde, where lambda tilde is the complement of the partition lambda into a suitable rectangle. So, what is the point? Here we have the solution of dual Yamanouchi toppling game. We have defined a notion of dual Yamanouchi word of type lambda, and again we have a solution for each standard Young tableau of a certain shape. But what is the point? The point is that each element in the toppling group can be presented as a product of a T lambda times the inverse of a T mu, or if you prefer, T lambda plus mu tilde. Again, it is not difficult to see. It is enough to refer to the reduced decomposition of G. So choose A in capital IN. This consists of non-negative integers, so you can always find a skew shape lambda minus mu. Lambda and mu are partitioned with at most n minus 1 parts. That in the ith row have AI boxes. So this explains you this theorem, and in terms of Toppling equivalence, this theorem says the following thing. When you have two equivalent configurations, then you can get the configuration, the final configuration beta, from the starting configuration alpha by performing a Yamanouchi toppling game, then a dual Yamanouchi toppling game. Clearly, it is not unique. You may do this in several ways. We can see what happens by referring to the Hasse diagram of our partial order. So we have two elements in the same orbit. We may consider the Hasse diagram obtained with respect to our partial order. We have a connected diagram. So by means of Yamanouchi toppling game, we move downward over this diagram. By means of dual Yamanouchi toppling game, we move upwards. So this is what happens when you want to reach beta from alpha by performing Yamanouchi toppling game. So I have also mentioned the idea to define the orbit series that in some way will encode the toppling equivalence, and in how many ways can we reach a fixed beta from a starting alpha by performing Yamanouchi and dual Yamanouchi toppling game. So what is an orbit series? You fix a configuration alpha. So an orbit series associated with alpha simply is a power series of this type. So for each beta equivalent to alpha, you have a monomial x to beta, and times are suitable coefficients that can be, well, an integer, polynomials, power series, anything. How we can construct an orbit series? Well, toppling group acts on z to the n, this being that in a very neat way it acts on monomials x to alpha. So we may also consider formal series obtained by where a given element in the toppling group occurs. Here we see a geometric series, and we can apply power series in the elements of the toppling group to some given monomial. So the idea is to find a certain power series in the toppling maps that acts on a given monomial x alpha and gives us some interesting orbit series. This is what we are going to do. We select a special family of elements in the toppling group. We have denoted Li and Ri. I goes from 1 to n minus 1. A way to think of these elements, these are algebraically independent elements. So assume to focus our attention only to elements once reduced decomposition are of type T lambda. Lambda is a partition. So consider the span over complex number, the vector space span over complex number by this element. This is actually a complex algebra. This is an algebra. And this algebra can be identified with polynomials in the Li. And another thing happens when we focus our attention on elements of type T lambda tilde. So the Ri generates this algebra. So the idea is to combine these elements in order to obtain a certain operator that we can see this way, theta ij, that depends on 4 parameters, and we apply the product of all theta ij for ij ranging from 1 to n with I less than j, and we apply this operator that seems to be a little complicated, but it's not too much, and to x to alpha. So the theorem is this is an orbit series, and we are able to explicitly describe the coefficient of each x to beta in the orbit series of any given alpha. This is a power series, and the coefficient goes as follows. So you want to know the coefficient of x to beta in the orbit series of alpha, you look at the unique element in the toppling group that send alpha to beta, then you write down all possible ways of writing G as a product of generators of type Lij and generators of type Rij. Then here you see D of A simply is the number of pairwise distinct Lij occurring in the factorization. D of B, the number of pairwise distinct elements of type Rij. S of A, the total number of generator Lij. S of B, the total number of Rij. Let me show you an example. So, assume we fix the complete graph. Here we have two equivalent configurations. The unique element sending alpha to beta is T1, T2, T3. This is the reduced decomposition. So, we are going to write down T1, T2, T3 as a product of Lij times a product of Rij. So we look at T lambda, which is L12, L34 to the square. So we have a total number of 3 generators of type Lij, 2 pairwise distinct. So we have a contribution of Q1 minus T1 to the square, Q1. If we look at T mu tilde, L12, R34, so 2 generators, 2 pairwise distinct generators. This is a contribution. And this says that this monomial times this monomial occurs in the coefficient of x to beta in the orbit series. But that's not the end. This orbit series, as I say, not only encode in some way the orbits, toppling equivalents, I mean, but also they encode principal order radial and dual principal order radial. I mean, I can specialize in a suitable way the 4 parameters, and all the configurations that are not less than alpha disappear from the series. And another thing happens if for another specialization, but that's not the end, because we also have a combinatorial description for this coefficient. They can certain decomposition of the R diagram of the unique lambda such that beta is T of lambda alpha. But now the question is, why symmetric functions? Well, we may associate x monomial x to alpha with a product of homogeneous, complete homogeneous symmetric function. This is a linear operator of Umbral type that occurs also in McDonald's book. So the question is, what about the symmetric function obtained by applying this operator to our other series? We have an answer for this case. So take this graph, this connected graph. After some computation, you realize that the elements Lij and Rij acts on configuration exactly in the same way that raising operators and lowering operators of McDonald's acts on vectors, arrays, of integers. So we have almost nothing to prove in this case. There is a star that shouldn't be there, but however, we can specialize in very different way our 4 parameter and obtain well, many classical bases of symmetric functions. Here we see the homogeneous, then the monomial. Actually, the case, well, the main fact is that we obtain all integral symmetric function. So monomial, sure, and these are Milne symmetric functions, a certain family of orthogonal polynomials with a nice combinatorial description in terms of representation theory, and Milne polynomials also are a special case of McDonald polynomials. So what we want to do is to understand if combinatorial description in terms of the toppling game can be given for all classical symmetric functions, and at this time we have an explicit combinatorial description for the expansion of all irreducible symmetric polynomials in terms of completely homogeneous symmetric function. So easy to see. We fix two configurations. The graph is the graph Ln that I have shown before. Then we detect the unique T lambda ascending alpha to beta, 2, 1, 0, 0. Then we decompose T lambda in terms of the Lij, count the occurrences again as and we have the coefficient of H beta in the expansion of the Littlewood-Richardson polynomials. But an analogous treatment can be done for any of the symmetric function I have shown before. So, as I said, the point is that we may deform the McDonald umbral operator in this way. Assume we have a probability measure. Assume that this probability measure has some moments, has its own moments, and define the operator in this way. Well, the remarkable thing is that the same orbit series, please don't care about the star, the same orbit series, specialized in a swivel way, will give you all classical orthogonal polynomial systems. When I say classical orthogonal polynomial system, I'm referring to the orthogonal polynomial sequence associated with a given probability measure. So Hermite, Laguerre, Poisson-Charlier, and so on. So exactly the same combinatorial stuff applied both to classical symmetric function theory, but to classical orthogonal polynomials. But the question now is the following. We are able to encode all transition matrices between symmetric functions in terms of toppling group. This is done by considering orbit series associated with subgroup of the toppling game. So we have an understanding in terms of the toppling game, or if you prefer, Yamanouchi toppling game, of many of the classical, well, about all classical interesting coefficients arising as transition matrices in the symmetric function theory. So constant coefficients, characters, LR, Littlewood-Richardson coefficients, and other things. So we want to understand if, well, a nice combinatorial treatment can be obtained for this stuff in terms of the toppling game, in terms of the configurations, and even more ambitious, we want to understand if a modified version of our operator can be defined in order to obtain the whole class of McDonald polynomials and to give a description of McDonald polynomials in terms of our games. But that's not the end, because the more exciting stuff is that all this relies on a special graph, only on a special graph that is, probably you have realized, this is the Dinkin graph of the symmetric group if presented as a Coxeter system. But we may change the graph. We may consider any connected graph. Then we may define an analog of raising operator and lowering operator for each graph. And we act on homogeneous symmetric functions and define an analog of, well, at this moment, of Littlewood-Richardson polynomials, Schur polynomials for each kind of graph. And so an understanding of the classical stuff may lead to, well, a general setting for a general family of polynomials associated with any connected graph. So that's the end. And many thanks.
Questions for Pasquale?
Maybe just a question to clarify something. When you talked about new polynomials, you mean the modified Hilbert polynomials, or?
Oh, that's a good question. I mean, you take McDonald polynomials in Qt, you set Q equal to 0, this gives you all little symmetrical polynomials. If you set the other parameter to 0, you obtain mean polynomials. That's a nice paper by Adriano Garcia.
Yes, so we get the modified for little.
It's that whole little with like conjugated, but yes. Yeah, that last comment that you had just struck me that isn't it like Ericsson had some other chip firing game on Lincoln diagrams that had to do. I mean, it's.
Yes, I have thought about this. You know, in some special case where you do not have any weight on the Lincoln graph, probably this could give you some well-known, we hope that this might give you the analog of shear function, for instance, for a different kind of constant system. When some weight occur on the Degree graph, well, not so easy to understand how, but we will see. It is in our plan.
Other questions or comments for Pasquale? Before we thank him again, let me remind you not to move a muscle, because we'll have the presentation of the best student paper following. Our applause for Pasquale. Thank you.
So before I let Richard actually take the stage, I would like to say a few things. So I'm here as representative, I guess, of the permanent committee, and many people have already been thanked for this conference, but not so much Richard. And before I do, I actually should tell you a little bit about how this all came to be. So 2 years ago in Iceland, so what we typically do, people on the permanent committee, when we have coffee or have a little chat with participants, really all we're doing is we're scouting. We're looking out for people who can organize the next conference. And so we were discussing and sort of thinking, well, where would we like to go? And Mike, where's Mike? There's Mike. And Mike said, I really like Chicago. So that made it easy because I'd scouted Bridget. And of course, at that time, I didn't know her so well. So I just walked up to her and I said, well, we really like Chicago and we think you're a really good conference organizer. And the response I sort of expected was a little bit like a man making sort of unwanted advances. But all she said is, yes, Chicago is a really great place and I do make a really good conference organizer. She was immediately very excited. The only thing she said, oh, I do have to talk to my dean. I can't quite remember the details. I think it was after the next talk. She said to me, yes, I've spoken to the dean and it's all ready to go. So quite amazing. And the most amazing thing is that you sort of kept it up. Because I think, was it yesterday or the day before yesterday, we were walking over and she said, well, I have to actually confess something. I really enjoyed organizing this meeting. So it's quite amazing. From 2 years ago up to now, she's still smiling.
You weren't supposed to tell anybody.
Well, no, you see, it is my task to tell you because, of course, there's future conferences. We've still been scouting. and in particular, to the younger people in the audience, I would like to say, before you apply for tenure track positions, please talk to Mike. Only go to a place that he enjoys. In any case, it's been great. We've been very, very impressed with all the work you've put in, and of course I know you've had a wonderful team, so I'm not going to try to name everyone, but yeah, it's been a pleasure, and thank you very much. We have a little card, and I think, Mike, we have a little gift as well. There it is.
Very kind. Now I'm going to change the topic completely. We're going to pretend that didn't happen. we've had a great time, I think, hopefully we all agree. And I've thanked a lot of people, and you've now thanked me, and something we haven't really talked about is just the quality of mathematics. And we've had, I think, some really amazing talks and posters and demonstrations and collaborations and conversations and all kinds of good things going on. And that's, largely thanks to the program committee, but even more so it's thanks to everybody who participated and submitted papers and asked questions and didn't ask questions but listened instead. And what we've come to do at FPSAC is present a prize for the best student paper presentation. And it's kind of exciting when graduate students, still before they finish, have come up and presented some amazing work. And typically we present one prize for that, and the program committee or the program committee chairs selects the recipients. And this year, the very special news is that they chose to split the prize. They kind of fell in love with two different student papers, so they've asked me to present them. And with a special note that these prizes for best student papers at FPSAC 2014 are being awarded both for the depth of the results and for the clarity of the presentations, which were impressive in each case. And so if Austin Roberts and Andrew Wilson are here, please come forward and congratulations. Washington, and he spoke about the expanding Hall-Littlewood and related polynomials, sums over Yamanouchi words, and Andrew from UC San Diego